So welcome everybody. Welcome to the OLLI brown bag presentation. And thank you for joining us today. If you have not muted yourself, please mute yourself for the presentation, and we will take questions at the end of the presentation today. If you want to put them in the chat, you can do that. If you would like to raise your hand at the end of the presentation, we can call on you that way as well. I also would like to thank all of the friends of OLLI. They are the people who make these brown bag presentations possible through their generous support. And yeah, like I said, we are ready to get started here. And if you haven't already muted yourself, please mute yourself. And we are going to go ahead and get started. So thank you for being here today.
Oh, okay.
Jane is going to do a quick introduction. Lori, she'd like to read your bio.
Okay, that's fine.
All right, Jane.
I get to praise your wonderful attributes, Lori. Lori, as we all know, probably from multiple presentations, multiple articles in the Times-Standard, etc., is an emeritus professor of geology at Humboldt State University. She has expertise in earthquakes, tsunamis, and hazard mitigation, right? Since retiring from teaching, she continues to provide scientific advice to the Redwood Coast Tsunami Work Group, engage in earthquake and tsunami outreach projects with the California Office of Emergency Services, and writes the Not My Fault column that appears in the Eureka Times-Standard most Sundays, including this last one. So here she is. Lori, welcome.
Well, thank you so much. Can everybody hear me okay? And hopefully my slides are showing.
Yes.
So today is a little departure for me. I'm going to be talking about human-caused earthquakes, but I will certainly put them in a context of what the next earthquake you're likely to feel will be. So I introduced this subject by two epicenter maps, one looking at the lower Midwest from 1970 to 2008, magnitude 2.5 and larger earthquakes, and the second from 2009 to the present. And it should be fairly obvious to everybody's eyes that there's a difference. And if you're not sure, then you can just look at what's on the side in terms of the number of earthquakes per year prior to 2008 and at the current. So something happened, and that's one of the things I'll be talking about today. So, all right, let's see. All right. Whenever I start talking about human-caused earthquakes, someone inevitably says, "Oh, do you mean fracking?" And my answer is no. I will mention hydraulic fracturing briefly a little later on. But hydraulic fracturing itself actually plays a very tiny role when it comes to earthquakes that people can cause. So just kind of tuck that in the back of your mind. Anyone who has ever heard me give a talk before knows that I always start with a slide that looks something like this. So if you decide you want to fall asleep in the next few minutes, this is what you need to make sure you keep in your brain. When the ground starts shaking, please stay where you are. Best to drop down to the ground if you can safely do so. If not, you want to stay sitting where you are. The important reason for that is that the majority of injuries in earthquakes occur while you're moving. And if you're down on the ground, you have a very hard time running out the door. So drop down, lift your arm over the back of your head and neck to protect it. If there's a sturdy table or desk nearby, get under it, hold on. Second point, know your zone. And hopefully, if you've been paying any attention to California's Tsunami Awareness Week, you've been hearing a lot about the tsunami hazard zones for our area. We've got easy ways to find out if you're in the zone just by going to the Redwood Coast Tsunami Work Group's website. If you are in the zone, shaking is your warning to go inland, to go to high ground. And once you are in a safe spot, please stay there. And you need to stay there for hours or until someone in official authority says it's safe to go back. Be aware of other hazards on our coast. We're very fortunate to be in a beautiful, beautiful place, and we can enjoy it if we respect Mother Nature. All right. So I want to start out with a few basics because it's important to know what an earthquake is and what we're talking about today. So in order to get an earthquake, we have to have some kind of stress acting on the rock, preferably what we call differential stress, which is stresses acting in opposite directions. And so the rock will deform elastically until finally we exceed the strength of the rock and it snaps and a rupture occurs, and that rupture surface is what we call the fault plane. And the two sides of the rock basically slip relative to one another, and the size of the fault and the amount of the slip is going to determine how big that earthquake is. We call that brittle rupture. Now, there are lots of vibrations in the ground that are not earthquakes. So if we set off an explosion, that's not an earthquake. It will produce vibrations on a seismograph, but it's not an earthquake. People are really good at creating all kinds of noise just by cars and walking. That's, again, not an earthquake. One of the most important tools of resource development is going out with a big old thumper truck and banging on the ground in order to look at the reflections and the refractions and figure out what's under there. That is not an earthquake. So I'm only going to really be talking about earthquakes today, forces that produce rupture or slip on a fault. Another important thing to remember, the overwhelming majority of earthquakes are caused by Mother Nature. It's her fault. It's not our fault. I'll talk about the few that are, but the overwhelming majority of earthquakes, and all of the earthquakes here on the North Coast, are caused by natural tectonic processes, driven by the heat coming out of the earth, driving the whole plate tectonic system and producing those stresses that result in brittle rupture. So I made a really rough calculation in putting this talk together, that there were on the order of 4,300 earthquakes in the US of magnitude 3 or larger in the last year. Only about 3% of those can we attribute to human causes. And that's just talking by the numbers. If we look at the larger earthquakes, 100% of them were caused by natural earth forces. In the last year, the two big US earthquakes in the lower 48 were two 6.5s, one in Western Nevada, one in Central Nevada. So again, Mother Nature, you can blame her for most of the earthquakes. If we look at that 3% or so of earthquakes that are not caused by Mother Nature, we find that there are a whole number of different causes. This was from one study that was done back in, I think it was done in about 2015, and looking at earthquakes that were caused what we call induced seismicity caused by human activity. About 37% caused by mining related activities. Another big chunk, nearly a quarter, caused by reservoirs, dams. About 15% by conventional oil and gas drilling. Another just under 8% by geothermal activity. 5% by injecting waste fluids beneath the surface. And finally, we get down to fracking there at about 4%. So 4% of the 3%, we're talking about a very, very small percentage of earthquakes. And then there are some other ones down there further on the list. So how do people cause earthquakes? Basically, 4 methods. We can add mass to the surface, and the easiest way to do that is by building a dam and having a whole bunch of water behind it. We can remove mass from the surface. We can squirt water down below the surface, water, other fluids into the ground, and we can remove fluids from the ground. All of those things can change stress and actually trigger earthquakes. So we're going to look at each one of these, some of them in more depth than another. So before we kind of jump into it, this is kind of as sciencey as I'm going to get in this talk, talking a little bit about rock strength, the depth under the ground, and where we see earthquakes. So the simple story is that obviously pressure increases as you go beneath the Earth's surface, just because of the weight on top of you. Anyone who's swum to the bottom of a swimming pool has experienced that pressure. So that pressure due to the weight, we call it the lithostatic pressure due to rock, makes the rock stronger as you get further down. That would happen continuously to the center of the Earth if it weren't for a second factor. And that's not only does the pressure increase, but it gets hotter. So heat tends to make rock more pliable, more ductile. And so there's a point at which somewhere on the order of 10 miles beneath the surface where the rock really becomes too warm for what we would call brittle fracture. Most of the Earth's surface, our earthquakes are at depths of less than 10 or 15 miles beneath the Earth's surface. There's an exception in subduction zones. And if Jane invites me back some other year, I can talk about those really deep earthquakes in subduction zones, but I'm not going to talk about those today. So we have both pressure and temperature. There is a third really important factor in whether we can get rocks to break, and that has to do with pore fluids. So I want you to think about a rock as being solid particles, and if I were to hold that rock up in the air, there would be spaces between those solid particles that we call pores. But if we happen to be down beneath the Earth's surface, those pores are probably going to be filled with water because we're below the groundwater table. It turns out the pressure of that water is really, really, and it's not necessarily just water, it can be gas as well, but it acts like a fluid. The pressure of the fluid in the pores can make a huge difference in terms of whether we can get a fault to grow, whether we can get the two sides of the rock to slip or not. So if you can kind of imagine, if I really pumped up the pressure in those pores, that sort of lifts the grains apart from one another and will allow them to slip, where if there wasn't that high pressure, they would be too locked together. So pressure the pore pressure is an incredibly important aspect in these human-caused earthquakes. So let me now just sort of run through these different cases. I'm going to start out with adding the mass, but we're going to add not just rock, we're going to add a great big pile of water beneath, behind a dam. And it's important to realize that we have two effects here. Not only are we adding the weight, but probably and more importantly, we're increasing the pore pressure. So that water is going to seep down beneath the reservoir, and it's going to increase the pressure in those pores. As a result, if there are already some existing stresses in the region, and there's really not a place on Earth where you don't have some residual stress, it may nudge those fault systems to failure, where in the absence of that pore pressure and that weight, it would be perfectly happy to sit there for another 100,000, 10,000 years. So earthquakes linked to the filling of reservoirs, and in particular, what seems to be most problematic is changing the level in a reservoir, and particularly in that initial filling. So I'm going to walk through a couple of examples here. The first time I became familiar with this reservoir-induced seismicity was after the 1975 magnitude 7.5 earthquake very near Lake Oroville in California. I was a grad student at that time, and there was a lot of interest in, oh, what had caused that earthquake? Because it was an earthquake in a place where we really didn't see earthquakes of that magnitude. The Oroville Reservoir was filled in 1967. Not very many earthquakes prior to that. And a 5.7 earthquake that caused minor damage. The general consensus in looking at the earthquakes as a function of time was that it seemed to be related to the filling of the reservoir. And in particular, between 1974 and 1975, it was the largest swing from it being very low levels to very high levels. And this earthquake occurred shortly after the peak in water levels. Partly in response to the 1975 earthquake, the proposed dam on the North Fork of the American River, the Auburn Dam, was not built, even though it was well into the development stage. In fact, there had been some construction. Every now and then, the Auburn Dam raises its head once again, and there are actually a number of large reservoir projects that are in the planning stages right now. And induced seismicity will certainly be part of the discussion. A far worse event that has also been linked to the filling of a reservoir occurred in India in 1967. This is the Koynanagar Dam, and an earthquake of magnitude 6.7 in 1967 caused an estimated 180 to 200 deaths. So very similar story to Lake Oroville, but I was able to find a really cool graph that sort of illustrates the story of these reservoir-induced earthquakes. Now, I know this is kind of a busy graph, so I'm going to walk through it. First of all, you'll see these red squares, and they represent the water level of the reservoir. So you can see that the water level goes down, it goes up, it goes down, it goes up. And that's typical of reservoirs because you fill them during the rainy season and you use the water in the dry season. So you are not only changing the weight in the area, but you're also fluctuating the pressure because basically the higher the water level, the greater the pressure. And it's interesting to note that very similar to what happened at Lake Oroville, we have really the largest swing from low to high right before we produce magnitude 6.7 earthquake. So these lines down here show the number of earthquakes per year. And you can see that there was a little bit of earthquake activity here in the beginning, but you're seeing that there's kind of an increase, and we get a pretty significant increase in early 1967, a couple of months before we get the earthquake. Now, since then, earthquake activity has continued. This is circumstantial evidence. We can't really prove it, but this is sort of considered the textbook example of reservoir-induced seismicity. A different sort of story takes place in Italy in 1963. Once again, we have a dam that is built. Construction begins in 1957. Filling begins in 1960. This is an area that has not experienced earthquakes in the past. And really right about the same time the filling occurs, small earthquakes begin to be seen. Not only is there a problem with earthquakes, but landslides are observed on the sides of the reservoir. Like earthquakes, landslides are also very, very sensitive to pore pressure. And so you change the pore pressure, you make it easier for layers of rock to slip. So the scientists were concerned, and a study in 1960 showed that, hey, it was possible they could have a really big catastrophic failure. But the momentum for filling the reservoir continued, and it was completely filled in 1963. More earthquakes and landslides, concerned enough that they lowered the reservoir level in September. That was not sufficient enough to prevent catastrophic failure on October 9th. One of the reasons I wanted to include the story of the Vaillant Dam is this is one of the most extraordinary photographs I have in my collection that shows the location of the dam here. And in fact, the dam is still there today. And here is where the landslide was. And you can see the sort of residual lake in the area. What happened was, so we have these earthquakes, and it's hard to say if the earthquakes caused the landslide or the landslide would have caused without them. But, earthquakes, landslide, this catastrophic landslide comes down here and creates an enormous tsunami in the reservoir with the water overtopping. You notice the dam is perfectly fine. I mean, the dam didn't fail. So the water overtopped, and unfortunately, there were a number of villages and towns downstream that were swept away. This may be the worst reservoir-induced earthquake. 2008, the magnitude 7.9 Sichuan earthquake that killed over 87,000 people, billions in losses, and evidence again is circumstantial. So here we have the dam, here we have the epicenter of the earthquake, and proximity, another area that was aseismic prior to the earthquake, and obviously ended up not being aseismic. So one thing I want to mention about these reservoir-induced earthquakes, and it's actually true of some of these other anthropogenic earthquakes as well, they're not acting on an area where there was no stress beforehand. So there's certainly some faults here. Eventually, given enough time, you may have produced a really big earthquake, but changing the pore pressures and the weight may nudge these things to failure more quickly, or potentially produce a larger earthquake than you would get if you had not been making these changes. The most common human-caused earthquakes are related to mining, related to removing mass in some way. Every year there are mine collapses, and sadly, every year there are casualties related to mine collapses. So I said, this is the most common cause of human monkeying with earthquakes. Most of these mining related earthquakes are really very small. An exception, the Newcastle earthquake in New South Wales, Australia, was a magnitude 5.7. And again, a similar story to what we saw with the dam related earthquakes. This is an area that no known faults beforehand. It was an area, I mean, one thing about Australia, it's what we call a stable continental platform. Australia is a really long way from the nearest plate boundary. So it does not tend to have the kinds of earthquake activity that we are accustomed to in, say, California. So what happened in the Newcastle area is there were coal fields, extensive excavation. For years, people had noticed deformation in the area. And when you create large tunnels, what happens is you affect both groundwater and the weight. And eventually the collapse related in really a significant earthquake that should not have killed anyone had Australia had decent building codes. But much of Australia has been developed with the thinking we don't have earthquakes. And as a result, weak brick structures tend to fail. Now, I'm throwing in underground nuclear testing partly because I find it really interesting, and it was something that I studied. In fact, my PhD dissertation was related to underground nuclear testing, and that could be a whole nother story for a talk sometime. But there are earthquakes related to underground nuclear testing. The test itself, when you set off a large explosion beneath the ground, whether it's in Nevada or whether it's in North Korea, the same physical sorts of things happen. So over here is a little diagram showing, the initial step when you have, you detonate the explosion, you have relatively intact rock all around, and then that explosion vaporizes. You get a pressure front and you vaporize the rock in a cavity. It creates this distinctive cavity with a lot of fractures. Now, the reason I was involved with this for my PhD dissertation, I studied a nuclear fracturing experiment that was done in the early 1970s to look at how effective nukes would be at fracturing rock to release gases. It turned out it was a dismal failure, and I won't get into details of that today, but it certainly produces fractures. But it doesn't just stay there. What happens then is you get this progressive failure of the cavity going upwards, and more rock forming until eventually it goes all the way up to the surface, and it creates a cavity. And you can all just go to Google Earth, like I did this morning, and search for the Nevada test site. And if you look in, you'll see the scars on the surface today. All these pock marks are the surface of these collapsed structures where the rock has collapsed. That is not an earthquake, but the change in the stress caused by all of this produces earthquakes in the vicinity. So it's a very characteristic pattern. The detonation of the explosive, which certainly records on seismograms, followed typically about a half an hour later by the collapse, which is also registered on seismographs. And then over a period of days, typically, you get a lot of small earthquakes around where that cavity formed. They don't appear to be significant in terms of causing damage or getting larger, but they certainly are a form of human-caused earthquakes. All right, we're going to change themes now and move into what I consider really the most important in terms of hazards, fluid-induced seismicity. So that's when we inject fluids down beneath the ground. And what do you think that's going to do? Well, it's going to increase the pore pressure. That's really the main thing that happens. And if you do this at a rapid rate and you do it for a long time, you can pretty significantly change the pore pressure, and that can lead to both more earthquakes and in some cases, larger earthquakes. So I'm going to talk about a couple of studies to begin with about fluid-induced seismicity. And the classic example every textbook will talk about is the Rocky Mountain Arsenal in Colorado, very near Denver, in 1962. So what do you think they do with the Rocky Mountain Arsenal? Well, they manufacture weapons. And it turns out that when you manufacture weapons, you use fluids and those fluids get contaminated. And you want to do something about them. You want to get rid of them. And so they had been just sort of storing them in reservoirs. Well, in the early days, they just poured it into rivers. Great, right? No, not so great. So in 1962, they decided, hey, it would really be preferable to get this stuff under the ground. So they drilled wells about 12,000 feet deep, and they started squirting the fluid down the wells. And this is really kind of a fun graph. So if we look down here at the bottom in orange, we're looking at the contaminated fluid injection rate, so millions of gallons per month. And almost immediately they started seeing earthquakes. And as they pumped more in, they got more earthquakes out. As they slowed down, fewer earthquakes. Some of these earthquakes were big enough to rattle people in Denver, and they were not happy about that. And so in 1965, they stopped doing that. I think they started tanking it to some, transporting it to some other location. But the result of what was observed there is the USGS then said, we need to really study this. And so they conducted an experiment in Rangeley, Colorado, about 200 miles to the west of Denver. And this was an oil field that had wells, some of which were not being used. And the USGS were allowed to use several wells to inject fluid down into them. And they had pressure sensors at depth, and they had seismographs, so they could really record in detail what was happening. And so this little graph here shows the number of earthquakes. So the total number of earthquakes are these open squares measured by seismographs all over the Rangeley site. The bars in orange are earthquakes that were within 1 kilometer of the well that they were squeezing the water down, forcing the water down into. And then this line shows the water pressure. So you can see the water pressure was fairly high, and then they reduced it. In fact, in some cases, they even pulled water out, increased it, decreased it. And you'll certainly notice, just like at Rocky Mountain Arsenal, the earthquake activity increases, decreases, increases, very closely related to the well pressure. And in particular, you see that the earthquake activity really close to the well, responds that way. There appears to be a threshold level over which, if you have the pressure above it, you get the earthquakes. When the pressure is below it, not so much. Now, you'd think that this data would have been used for the next part of my talk, which is a different sort of experiment in fluid-induced seismicity. And this takes us to the lower Midwest and waste fluid disposal in deep wells, and what we've learned as a result of it. So prior to 2009, the waste fluids from drilling operations, and let me make it clear that when you are drilling for hydrocarbons, you use a lot of fluids. You need fluids to drill the holes. You need fluids to continue to pressurize the system. And it's nasty stuff. You don't really want that sludge just lying around on the surface. And prior to 2009, pretty much that's what happened. So in 2009, regulations are passed to require that all of these nasty fluids be disposed of in deep wells. There are a lot of them, estimates of at least 100,000 of them in the US. It's proprietary information. It's hard to get a hold of exactly where they're all located, but there were certainly consequences, not everywhere. And in fact, very few wells proved to be problematic, but they certainly were in Oklahoma. So if you kind of look here, and I think if I go to this next, yes, there are a number of seismic hotspots. If we look at the earthquake activity post 2009 compared to beforehand, we see that there are, particularly in Oklahoma, but also in the Dallas-Fort Worth area, over here in West Texas, Odessa, Midland area, and even in southern Kansas, central Kansas, there have been some spots elsewhere. So another way to look at this is the number of magnitude 2.5 and larger earthquakes since 2000. So yes, there are earthquakes in Oklahoma. a handful a year of 2.5 and larger. But you can see that things really start to change right around here in 2009. There's a kind of a slow increase and then a very rapid increase up until about 2015. Then it looks like it's beginning to bend over. What has caused this? Well, this is the point right here where the waste fluids start being stored underground. And this is the point of the real oil shale boom, where hydrofracturing actually becomes part of the story, but not because of the fracking itself, but because there's now a lot more fluid to dispose of. So it's the waste fluids associated with hydrofracturing, not the hydrofracturing itself, that creates the problem. And in Oklahoma, things were completely unregulated up until right about here, when finally it begins to be a real concern. Now, another interesting way to look at this is to compare Oklahoma and California. So prior to here we have 2009. I mean, 2008 and earlier, clearly California has more felt earthquakes than any place in the lower 48. And it's fairly steady, somewhere on the order of around 200 per year, some years lower, some years, as we'll see in a moment, quite a bit higher. But Oklahoma starts in the race and gets a little bigger, a little lower, and then boom, 2014, 2015, 2016, even 2017, Oklahoma has more felt earthquakes than California. I could count when I do my daily earthquake update, just about every day I'd be talking about a magnitude 3 or larger earthquake in Oklahoma. The problem was that not all of Oklahoma's earthquakes were small. There were 4 in the magnitude 5 range, and 2 of them actually produced a fair amount of damage. The 5.7, November 5th, 2011, and the 5.8 in September of 2016. And the problems were mainly to these brick structures, which is always the problem in modest earthquakes. They don't resist that shaking strength. But at this point, the insurance companies started filing lawsuits. And if you want to make regulations happen in a place like Oklahoma, there's nothing like getting lawsuits. And as a result, in the summer of 2015, Oklahoma enacted legislation that restricted the rate at which these waste fluids could be pumped into the wells and the total volume. And the result really was significant. So here's that same graph again. There we're looking at Oklahoma's glory years for earthquakes to 2014 to 2016. Since then, we've seen a steady decrease. Now, there's another thing that's been happening in 2019 and 2020, and that is we have an oil glut, and the actual drilling operations have substantially decreased. Now look at what California's done. Boom! What do we have in 2019? Well, we have a Mother Nature caused earthquake. We have the Ridgecrest earthquake, magnitude 7.1, that is still producing aftershocks to this day. So it's kind of an interesting little comparison there. Induced seismicity is now included on USGS hazard maps. So this shows a map of all of the areas of wells. So all of these gray areas are places where there's deep disposal of drilling fluids. Notice that only a few of them are associated with an increase in seismicity. And clearly Oklahoma in particular, there are a few other areas here. So if you look at the latest USGS hazard maps, and over here on the right, it compares the natural seismicity in California, because in California, we don't have that issue. Mother Nature just produces all of our earthquakes. And then you look at the new maps, hazard maps in the Oklahoma area that now do include this induced seismicity, making it almost as likely in many areas of Oklahoma that you'll experience strong shaking as you will in California. So I am winding up a little bit more on fluid-induced seismicity, and then I will get to the geysers. So I did say that hydrofracturing itself can produce very small earthquakes. And over here on the right is a little illustration of how hydrofracturing works. You drill down, you create a horizontal conduit, and then at very high pressure, you squirt fluids into the surrounding oil shale. Now, those squirts last for a very short amount of time. And the whole time you're going to be working in an area, a particular line, is on the hour of hours to at most days. This is in contrast to these disposal wells, which will continue to be used for decades. So you can kind of imagine that in hydrofracturing, we really don't change the pore fluids. We don't change the pressure. Small amounts of fracturing close to the hole. Obviously, the nasty fluids that you've used, they then get forced down into these deep wells where they can trigger significant earthquakes. So the USGS, basically, the bottom line is fracking itself is not the problem in terms of inducing earthquakes. Lots of other issues I'm not going to get into here, but it doesn't trigger the earthquakes, but the disposal of the fluids definitely can. The next time you hear of a strongly felt earthquake, don't immediately assume it's because there was a deep disposal well there. It probably was not. It was probably due just to Mother Nature. Now, the process of pulling fluids out of the ground can also trigger earthquakes. In fact, if you look at every conventional well site, oil well site, you basically find small earthquakes. You're changing the pore fluids, you're changing the stress. As a result, that can produce earthquakes. No direct hydrologic pore fluid really is required. These tend to be very small. I want to kind of finish up talking about the Geysers geothermal field, which is what I call a hybrid example of both removing fluids and injecting them. So the way geothermal fields work is that we pull out the hot water and we use that heat to drive turbines and produce electricity. There's always some kind of recirculation because you pull the water out, it's cold, you squirt it back down. So from the very beginning of a geothermal field, there is both removing the fluids and injecting them. At the geysers, it's a little more complicated. So let me give you a very brief history of the Geysers geothermal field. It's natural, a natural area of hot springs that certainly has been utilized by the native peoples in the area for millennia. In the 1850s, a lot of development in the Calistoga area, spas and resort hotels making use of the natural hot springs. 1921 is the first known use of the geothermal energy for electricity production, and it was at a hotel where they basically used the heat to create enough electricity for the electric lights in the hotel. In the 1960s, PG&E gets into the act, and the first geothermal well for really statewide consumption is developed. And that continues to be developed until nearly the turn of the century. I mean, it's still developed today, but in 1998, Calpine took over the management of the geothermal field. 2004 is an important point because an extra dose of injection is provided when a wastewater line from Santa Rosa is built to inject those fluids directly into the reservoir. Why? Well, I'll try to get into that. This looks at the production of energy and the reinjection of fluids up until just about the turn of the century. And you can see that development is ramping up, and it reaches kind of a peak in the mid-1980s. And then it starts decreasing. And the reason it's decreasing is really because we're depleting the resource. We're pulling out more hot water than Mother Nature can heat up naturally due to contact with a magma body at depth. So we've removed too much fluid. Now, there has been reinjection all of this time of basically the water that was left over. And that continues, but in the 2000s, it's decided, let's beef up the system by increasing the rate at which we're putting water back in. So here's another graph, but it now goes to 2005. And a very important right here, this is when the Santa Rosa pipe gets built. Also on this graph, the green line are earthquakes of magnitude 1.5 or larger. And up here in the top are earthquakes that are likely to be fairly widely felt regionally, magnitude 4 and larger. So a couple of things you can see from this is that we really didn't have earthquakes before the geothermal facility was built. The earthquakes really start with the withdrawal of the hot fluid. Probably the injection doesn't make a huge role down here. It starts to make more of a role when there's more injection going on. And you can see this in the little graph I put together. Earthquakes per year, and I started with magnitude 0 and larger, that we have a pretty good record in this area from 1980 to the present. And you can see there's a lot of them. This is 2,000 earthquakes. So in 2011, we had about 19,000 earthquakes of magnitude 0 and larger. And this is where the Santa Rosa waste fluid pipeline was drilled. So I'll just stay on this one a little bit longer. So what we see at the geysers is, in a sense, an ongoing experiment where we know very well the rate at which the fluids, we know where the wells are, we know where the rate at which water is being pumped into them. We have lots of seismographs. So unlike what's happening in Oklahoma and in much of the Midwest, where we don't have any idea how much fluid is actually, or even precisely where those wells are located, or how much fluid is being pumped down. The Geysers Geothermal Area provides provides data that become very important for injection of fluids worldwide. Okay, I think I've thrown out enough just kind of general information. I want to leave you with a few final thoughts and then let you throw questions at me. There's no question that human activities can cause earthquakes, okay? Most of the time, it's related to fluid pore pressures. That's the real important thing. I'm just about 100% sure that the next earthquake you feel will be the result of natural forces. Now, if some of you happen to live in the Geysers Geothermal Area, you might feel a 4 that's related to the injection process. If you're in Humboldt County, the next earthquake you feel will be caused by Mother Nature. And I am absolutely sure that there will be earthquakes today, tomorrow, next week in the Geysers Geothermal Area. If you look at the seismicity maps of the state, and if you change the setting to be all earthquakes, not just earthquakes of 2.5 and larger, you will always see the Geysers geothermal field light up like a little hot spot. And time for questions. And those of you who do follow social media, please follow the Redwood Coast Tsunami Work Group and Kamome, the Boat of Hope. And I'm ready for questions.
Thank you, Lori. That was great. The first question is actually, what is the link to the Tsunami Work Group website?
Well, the Tsunami Work Group website is rctwg.humboldt.edu. But all you have to do is just Google Redwood Coast Tsunami Work Group and you'll get there.
Great, thank you. What is the occurrence of earthquakes when the water lowers dramatically in a drought year?
You know, it's not so much the water lowering. The bigger problem is when the water then raises again. So it's, there are subsidence effects. So when you continually pump water out of an aquifer, you may get small earthquakes related to the fact that the ground is just lowering. But the bigger problem is when you get the wet year again and you start increasing the water and that pore pressure increases. So you can kind of think of it as it's not really lubricating. Just because it's wet doesn't mean it's lubricated, but it's lifting the particles apart and it's making it easier to slip.
Okay, and isn't there a concern that a geysers quake will trigger a quake along a more major fault?
You know, that's a really good question. And the good news is that we actually have a lot of data. So, you know, we've been seeing this seismicity in the geysers area since the 1960s. The closest, and there are significant faults in California. The Mayakama-Rogers Creek fault system is about 6-8 miles away. absolutely zero evidence that what is happening in the geysers has affected anything on the Mayakama Fault. And it's well instrumented. There's been an ongoing spurt of interesting earthquake activity near Willits on the Mayakama since August. There are various different little hotspots, absolutely nothing that we can correlate with what's happening at the geysers. Now, there are some geysers earthquakes that get into the magnitude 4 range and are certainly widely felt. There have been magnitude 5s in the region, but not really. I think there may have been one magnitude 5 that's directly associated with the geysers, but we're just not seeing anything like what we see in Oklahoma. So, which is interesting. That and that has certainly been a subject of a lot of study, is why do we see that really pronounced elevation in seismicity in Oklahoma that we certainly don't see in California. And it's hard to really get a good answer on that, partly because the data is proprietary and it's difficult to really get in there and study it. But the general explanation is that, you know, I mean, if there are active fault systems in Oklahoma, and if you looked at the map of Oklahoma earthquake activity prior to that, there were earthquakes there. And so the general explanation is that the increase in pore pressure was enough to nudge these pre-existing systems to failure, where that has not happened in the vast majority of these deep injection well sites. As I said, there's something on the order of 100,000 injection wells in the Midwest, in the US, and in Canada. And fewer than a dozen have really shown to be problematic in terms of triggering earthquake activity. So there's something very special happening in those places where we see the induced seismicity.
Thank you. Similarly, if a dam is decommissioned, would that also influence quake probability?
Again, it has to do lowering, like the filling of a dam with sediment. So if you're thinking of those dams on the Klamath that have almost no capacity left anymore, that's not likely to be a problem. Emptying a dam and leaving it empty doesn't seem to be the problem. The problem seems to be filling the dam and then fluctuating the water levels. We had some concern in a couple of years ago, what was it, 2017, when the Oroville spillway was damaged, and then the reservoir was significantly lowered gently lowered. And there was some concern as they did that repair and then refilled it, that there could have been an increase in seismicity. Didn't observe it in that particular case.
Interesting. As we drive along cliff sides, we can see curves, waves, and swirls in the rock formation. Are these formed at least 10 miles below the Earth's surface?
Yes, they're formed. Well, it's hard for a lot of what you see in Humboldt County, especially the really beautiful curvy chert that you see exposed on, you know, Trinidad Beach and many of our beaches. That's occurring, that deformation is probably occurring very, very, very far offshore and probably not super deep. That chert is formed by the deaths of a gazillion microorganisms, radiolarians, diatoms, little silicic rich. I mean, the graveyards of an incredible number of tiny creatures. And as they die, they rain down on the seafloor, and then they get buried, and they're very easily deformed before it becomes solidified. And so a lot of that deformation is probably not that deep. It's just way far offshore, maybe on the order of 1,000 feet of burial. And then they're sort of oozy, and they're easily bent into spectacular forms. So by the time they get completely solidified, they're actually too brittle to deform that way. So some of what you see may be deformed due to the temperature and pressure at depth. Some is some of the wild stuff that happens in those earlier depositional stages far offshore.
Great. In San Diego County, 2 reservoirs, I'm told, are on the same earthquake fault line, San Vicente and El Capitan. Is there a concern? If both burst, all will go down San Diego River, Mission Valley. Your thoughts?
Oh, there's a huge concern about dams and dam safety in California. The classic story of the Sheffield Dam in Santa Barbara that failed in an earthquake. I think that was in the 1930s. But, and we were very fortunate in 1971 in the San Fernando Valley earthquake that major ruptures in one of the dams very close to failing, and it did not. This is, you know, earthquakes and dam safety, whether natural dams or artificial dams. And let me mention that when we have big earthquakes, we get big landslides. And if you've ever rafted down any of our rivers, you can see the remnants of these huge landslides that in the past blocked parts of the Smith River or parts of the Klamath. And when you get there's always a potential of, in fact, these natural dams are really worrisome because obviously we can't control them. I think it was the Sichuan earthquake. There was a big concern after, not from the reservoir itself, but from, you know, one of these landslides. So yes, the answer is one always has to be concerned and continually monitoring the you know, structural integrity of dams, of looking at the seismic hazards in the area. And we need water. It's always a trade-off between, you know, needing the water for all kinds of reasons and any potential hazard.
What do you say about the assumption that earthquakes are bad and should be avoided attitude? What do we really have to worry about here?
Well, earthquakes can't be avoided. There's not a place on the planet that has not experienced strong shaking. And so that's something you cannot avoid. However, we know how to live with earthquakes, and we can engineer structures to resist ground shaking. We can be very careful with where we locate critical infrastructure. I like to give as an example the Alaska pipeline and how it goes across numerous incredible, huge faults in Alaska. And there was debate when the pipeline was being built to, you know, identifying the fault zones, and a real interesting engineering solution came up of basically making these big bends in the pipeline and putting them on movable train rails so that, when the two sides of the fault moved, the pipeline could just move with it. And as a result of the Denali earthquake, what was that, 2001, somewhere around then, that was 7.9 earthquake, huge amount of surface rupture. And there was no damage at all to the Alaska pipeline because they had put in the extra expense. I mean, what would have been a disaster, rupturing right through, high oil fluid, oil pouring out onto the sensitive ecosystem. But it wasn't even a story because it wasn't a disaster, because we put the effort into the science to understand where the faults were and how it needed to be designed. So it is possible to build buildings, to build infrastructure that can withstand strong ground shaking. But we have a real problem of aging infrastructure, and especially in places, California is actually pretty darn good because we've had earthquake resilient design going back to the 1930s. You go to a state like Oregon, which wasn't even aware they had an earthquake threat until the 1980s. So in Oregon, you have, the majority of your infrastructure and your buildings are all built with essentially very weak seismic codes, and even schools. So in California, we've had laws since the 30s about, earthquake resistant design in schools. In Oregon, you still find many schools that are built of unreinforced brick. So it's a continued problem. And unfortunately, we usually don't do anything until after a disaster's happened.
True. When new dams are planned, what studies can be done, if any, to predict new seismicity in what had been seismic areas?
Okay, this is certainly not my area of expertise, so I'm just sort of throwing out some general ideas. So, and certainly this is, done when looking at potential new dam sites in California. You look at historic seismicity, you do a very detailed study of geologic study, you do boreholes, you look at the three-dimensional structure of an area, and by putting all those things together, and then you do models. So, on a computer, you put in a certain, volume of water, and you make an estimate of the changes in the pore fluids. And in the process of obviously of filling a reservoir, you very, very carefully monitor that. There are a lot of reservoirs in the world. There's actually a lot of data. So you're basically compiling all of that information and keeping on track of it.
Does difference in substrate cause different effects of increase in pore pressure?
Oh, absolutely. Certainly the volume of the pore pressure, the pore spaces becomes important, but also how things are layered, that you might have a zone that has fairly large porosity and then a zone with very low porosity. You have to look at the whole structure, how easy it is for fluids to flow in and out of an area. So all of those things become really important in looking at the flow of fluids. There are lots of people out there who know a whole lot more about that than I do.
In another water-related question, Are there areas where sea level rise might trigger quakes because of the increased weight? And if so, what areas around the world might be most vulnerable to that?
That's a good question. Probably because the sea level rise is very uniform, it's not creating what we call differential stress. When you fill a reservoir, you're putting high pressure in one area and an area outside of it that does not. And so you've got, the differential stress. Sea level rise itself, the biggest issues are really geomorphic. So what happens, the erosional concerns, what happens to base level with river systems, what happens to groundwater. There's certainly an awful lot of issues having to do with fluids, but that's happening very shallowly. I am not aware of any studies that have really looked at, general seismicity related to sea level rise.
What is the relationship between rock type and earthquake activity, particularly resulting from fracking and injection wells? Do California and Oklahoma have similar underground rock types?
California and Oklahoma are about as different as you could possibly imagine in more ways than one. I mean, no, we have sedimentary basins in California, and we certainly have, hydrocarbon extraction. It's been going on in California for a long time. But we don't have the sort of massive oil shales that you have in Oklahoma. We're not going to see a great dive into oil shale development in California, because that's not what we have here. So what was the other part of that question?
Is the relationship between rock type and earthquake activity?
Yeah, I mean, the thing with earthquake activity, earthquakes are happening at depth. Okay, the average depth of where that earthquake nucleates is miles beneath the surface. When we look at the San Andreas Fault, we find that there's very distinctively different behaviors in different parts of the fault. We find areas of the San Andreas Fault which are creeping, which don't seem to be strong enough to really get a whole lot of strain accumulation and produce a really big earthquake. So we call the area that's sort of south of the San Francisco Bay Area the creeping section, where they can't even keep the streets paved because that slow creeping motion keeps producing cracks. Whereas there are other parts of the San Andreas system that are just locked tight, that don't even produce small earthquakes in between the really big ones. We kind of attribute that to changes in rock and maybe fluid pressures, because they're the really important trigger at depth. But it's very difficult to really parse all of that out, because we can't sample 10 miles beneath the surface. We might sample a mile beneath the surface, or 2 miles, but we really don't have a good way of thoroughly monitoring what's happening down there at depth. So yes, rock type is probably important. Fluids are really important. Obviously, the whole geometry of the stresses and so forth are important.
Okay, why is the Geysers field where it is?
That's wonderful. I kind of got into that in a couple of my columns last fall. So the Geysers Geothermal Area is there because there's a buried magma body, molten rock is beneath the surface, and that molten rock is part of the Clear Lake volcanic field. So you can see Mount Konaktai. It's a composite volcano that's very young that will erupt again. And you can see a lot of volcanic features in the Clear Lake area. Now, up until a few decades ago, it was kind of head scratching as to why there's a volcanic field in Clear Lake. I have a very close friend from grad school did her PhD dissertation on the Clear Lake field. And at that time, there wasn't a really logical explanation. Now we actually think it's related to the growth and development of the San Andreas Fault, and not the fault motion itself, but what has happened as the Mendocino Triple Junction has moved north. And basically, the really short arm waving explanation is that as the Triple Junction moves north, now we know that about 12 million years ago, the Triple Junction was close to San Francisco, the Bay Area. And the Triple Junction was born about 30 million years ago, close to where Los Angeles is. And it's proceeding to grow north. But as it grows north, it creates sort of a wake of stretched and thinned crust behind it. And basically, the Clear Lake volcanic field is in that stretched zone. Think of it as Mother Nature's stretch mark behind the moving Mendocino Triple Junction. And that brings up an interesting notion is, are we going to see the volcanic zone sort of move to the north as the Triple Junction continues to move to the north? Unfortunately, I won't be able to give you the answer to that because it's going to take another 10, 15 million years to be able to sort of see what happens. But basically, we now think it's a result of the deformation, the sort of stretching, the thinning, the fact that the mantle, hot mantle material gets much closer to the surface in the wake of the Triple Junction.
All right, thank you. There is also a lot of very distorted layers and huge boulders inland on the Van Dusen and as far east as along Highway 36 near Red Bluff. Are those still formed offshore originally?
Well, when you look at what's in our rivers, it's a real, I mean, you're kind of seeing geology in action. You're seeing rock types that were formed inland in the roots of our great mountain chains. So when you see a lot of the metamorphic rocks and the granitic type rocks, those were the cores of old, volcanic features. So in the Klamaths, the roots of the Klamaths and the Sierras. And so there are rocks that have come from, rocks and sediment that have come from way far inland, possibly as far away as Idaho, where they may have started out before they kind of made their way here. And then some of them have been recycled in this complex process in subduction zones where the stuff gets pulled under and then some of the stuff comes back up. So we have quite an extraordinary mixing of rock types when you look at what is in our stream channels and along our beaches.
Well, Lori, I also wanted to make sure that you get a chance to look at the comments because there are a lot of very kind compliments to you.
I'll definitely do that when I get
and then there is one more question that I see. Is there a likely increase in earthquake activity due to climate change?
Not that I know of, and we wouldn't really expect it because earthquakes are driven by heat within the earth. We have absolutely no evidence of earthquake weather, of there being, as I say, yeah, there's earthquake weather. It can be freezing, it can be boiling, it can be anything in between. Any weather is earthquake weather. And that's simply because what we call kind of the skin depth, the earth is a really good insulator. It's the fluctuations in temperature at the surface, they don't get down very deep, and they certainly don't get down to the depth where earthquakes are generated. So climate change can certainly increase our hazard because more and more people tend to be concentrated in particularly vulnerable areas, coastal areas, living on land, on weak hillsides and things like that. But in terms of driving the number of earthquakes itself, if you look at earthquake activity as a function of time, going back a century or two, there's absolutely no correlation with what's happening at the surface. In contrast to looking at the size of hurricanes and the frequency of floods and those sorts of things, very clearly related to climate change, but not earthquake activity.
Earthquake. And then one more question came while you were talking. I understand that the Earth is expanding over time. Is the Earth heating up and the magnetic field coming closer to the surface generally?
First of all, the Earth is not expanding. So there was a debate about that for a number of years. In the late 1800s, there was a debate about whether the Earth was expanding, and what the shape of the Earth was, whether it was an oblate spheroid or a prolate spheroid. We have really good information about the shape of the Earth. It's the field of geodesy. And thanks to all those satellites going around, we know the shape really, really well. And it is not expanding and it is not contracting.
Well, I think that is it for questions. I would like to thank you again for this amazing presentation. It is so informative. And as I said, there's a lot of very kind comments for you in the chat.
Good. Thank you so much. And thanks for asking me. And it's kind of nice to look into something a little different.